Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together. Welcome to exponential functions and their key features. One thing I want to keep in mind with exponential functions is kind of the format of how they're written. You're going to see them usually in a times b to the x. So this is really important to note here that x is our exponent, okay? So we're always going to be multiplying by b. So let's go ahead and let's just kind of look at something and see what happens here. Let's go ahead and do 5 times 2 to the x. Okay. Well, if x is 0, if you utilize a calculator, anything to the 0 power is 1 times 5 is 5. 5 times 2 to the first is 10. 5 times 2 squared is 20. 5 times 2 cubed is 40. 5 times 4, 5 times 2 to the fourth is 80. Do you see a pattern happening already? If you said, yeah, times 2, you're exactly right, and that would be because our base is 2. It's kind of like mitosis, right? Like if you started with 5 cells and they jumped up to 10 cells, they'd split to 20 cells and they split to 40. Maybe these are million cells, right? Okay, so what happens if we go back in time? -1. Well, what would have to come before 5? It would be 2.5. -2 would be 1.25, right? And then we can keep going and keep going and keep going and backwards. Will it ever equal 0? And the answer to that is no. So why would that be? Well, let's say you have a piece of paper and you tear it in half. Sorry, the paper on the edge was sticky. And then you take that paper and you tear it in half. And then you take that and you tear it in half. And you tear it in half. And you tear it in half. I'm not doing perfect halves, I get that. And you tear it in half. And you tear it in half. Am I ever going to be out of paper? I might be out of paper I can hold in my hand, but am I ever actually going to get to no paper? It'll round to no paper, but it'll still be microscopic scraps, right? Might need an X-Acto knife, things like that, right? But eventually we're just going to say, it's about 0. Okay, so with that in mind, our domain on these is -infinity to infinity. But our range is 0, not included, to infinity. And we have a horizontal asymptote at y equals 0. And our ordered pair will always be 0, comma. Anything to the 0 power is 1. 1 times a is a. So those things are going to hold true unless we have a plus or a minus sign, right? That shifts it. For the basic a times b to the x, we're going to have that hold true, assuming that it's written in this form. If it's been shifted left or right, up or down, that will adjust. We're just focusing on this basic format. And again, the reason why it's called exponential is because our variable is the exponent. Okay? A lot of times we see this kind of stuff in exponential growth. I talked about mitosis, exponential decay. We can see it with radioactive decay. We can see it with half-life problems as far as using the inverse of exponential functions. So the graph generally looks like, and I'm going to kind of do this rough sketch because the slope takes off and grows really, really quickly, as you noticed. So a lot of times when we're graphing these, we might want to go 1, 2, 3, 4, 5. But here we might want to go 10, 20, 30, 40, 50, 60, 70, 80, right? Because while 0 was at 5, 1 was at 10, 2 was at 20, 3 was at 40, and 4 was at 80. So we're getting this wildly quickly growing with that horizontal asymptote. Now, why would this be called exponential growth? Well, it's because as you moved left to right, the graph was going up. How could I tell from the equation before it started that it was going to be growing? Well, if I multiply by anything bigger than 1, the answer gets bigger, right? So when your b value is greater than 1, you get exponential growth. And here, remember this quadrant is positive, comma, positive. So as x approaches positive infinity, y is approaching positive infinity. Now this axis, this arrow right here, is at a negative number and about 0, correct? So over here we would say as x goes to negative infinity, y approaches 0. And so if they ask you to describe end behaviors, that's what they're asking for, is these little descriptions. Again, this ordered pair is basically positive, positive. This is basically a negative number 0, hence why we have what we have here. And that goes right along with our domain and reals, okay? So exponential growth, probably only going to take 2 quadrants or whatever. If b were less than 1, but greater than 0, we would have exponential decay. Think of multiplying by 1/3, okay? Let's start with 99. Okay. If we substitute 0, 1/3 to the 0 is 1, times 99 is 99. If we do 1, 1/3 to the first is 1/3 times 99 is 33. If we put in 2, 1/3 squared is 1/9, so that'd be 11. So do you see how it's kind of like it's dividing by 3 each time? It's because we're multiplying by 1/3. So 3 would be 11/3, so on and so forth. But we would still have that horizontal asymptote. It's just 0 would be at 99, 1 would be at 33, 2 would be 11, 3 would be... So now see how we're coming down? Okay. Now I will tell you, side note, 1/3 is equal to 3 to the negative first. So could they write it as 99 times 3 to the negative x? Absolutely, because that negative is with the x, it would flip it horizontally. Same thing as an exponential decay. So these two are actually saying the exact same thing. They're just written in different formats. So we have to be careful with that. But when we have a positive x and our base is between 0 and 1, we'll have exponential decay. Our horizontal asymptote is still at y equals 0. Part of that basic science principle of matter can neither be created nor destroyed. Okay. So, just a refresher and a connection. If you had something like 3 to the x versus 3 to the x plus 2 minus 5. Okay, we'll look at the domain the range, and the asymptote as well, the horizontal asymptote. So the domain is negative infinity to infinity here. The range is 0 to infinity, and y equals 0 is the horizontal asymptote. Over here, the HK shifts still apply that have applied in several other of my videos. We're moving left 2 and down 5. Well, if you're on negative infinity to infinity and you move left 2, aren't you still on negative infinity to infinity? Yes. So the domain is still negative infinity to infinity. But now we've moved it down 5. So these have to drop down 5. The horizontal asymptote is now at y equals negative 5, and our range is now at negative 5 to infinity. So again, all those values still keep in mind, things like that. We can always, always, always use our HK shifts. Okay. So this exponential decay, things like that, radioactive decay, they usually follow along the lines of something to this effect. Okay? And A will be your beginning amount. When t equals 0. R is a percentage that you rewrite as a decimal. And T is going to stand for time. Now it's important that if your percentage rate is in months, your time is in month. If your percentage rate is in years, your time is in years. So make sure you are using apples to apples, okay? So let's say you purchased a car. And you purchased this car for $32,000. Okay? However, the car usually, this type of car depreciates 10% a year. What will its worth be in 5 years? Now, if you tell me that, well, 10% a year is $3,200, so you just take off $3,200 for 5 years. Well, the problem with that thinking is if I keep doing that, once I hit 20 years, your car is worth negative money. That's not how that works. You always at least have scrap value, right? So that's why we're using this kind of thing. So depreciating means go down. So the worth of your car in 5 years will be $32,000. 1 minus, because we're depreciating, 10%, so that's 10% a year. Notice a year and 5 years. And we'll put in 5. Now, your effective rate, 1 minus 0.1, is really, because I want to know what your remaining car is worth, not how much you lost that year. So if you lose 10% a year, you keep 90%. So that's kind of how that's going in there. Okay? So if you type that into a calculator, you're going to get $18,895.68. So keep that in mind that if you ended up borrowing money and you still owe $24,000 on your loan and it's only worth $18,000, you might want to pay off more at a time or something, right? But it's very important to understand that if something is going up, it's going to be a plus. If it's going down, it's going to be a minus. Doing it this way saves us from going, okay, 32,000 times 10% is 3200. So after 1 year, 32,000 minus 3200. Right? Yep. So that would be after 1 year. So then you'd have to take off 10% of that. After 2 years, this time we'd be subtracting 2880. Okay, so on and so forth. We'd have to do that because you lose less in your second year than you did your first. The formula is a much more efficient way. So please keep that in mind. And sometimes with these, they do like to go ahead and have you compare some average rate of change. So keep in mind that if they're asking you to change, they might say something like, on the interval, does F or G have a greater rate of change? I should say average rate of change. This just really means slope. Who has the better slope? And they're giving us two x values. So let's say f of x is 3 times 2.1 to the x, and g of x is 2.1 times 3. So it's really going to change. It's really going to change on our interval which one's the better, because some of them are going to be better in this window, some are going to be better in this window. They're specifically giving us 2 to 7. So we just 2, 7, 2, 7, 13.23, 540.326, and that continues on. 18.94592.7. We can see right here, 18 to 4,592 is a bigger growth than 13 to 540. So we can already tell that G has the greater rate of change on this window. Could we go ahead and find the full slope? Yes, the slope of this one is approximately 105, and this is approximately 915. So again, average rate of change is just slope. If you make a table of values for the beginning and end of your interval, you can usually compare these. Exponential growth does have a varying slope, so you have to make sure you know which two values you're working on. Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? And drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.